be here this morning, and I hope to share some of the adventure of the OSIRIS-REx mission. We had a fantastic year last year, arriving at the asteroid a little over a year ago, and we spent all of 2019 mapping the surface of this amazing object, trying to find a location on the surface where we could send the spacecraft down to make contact and collect the sample. So you can kind of see the outline of the vehicle here on the left of the title slide. It's a spacecraft that was built by our partners, Lockheed Martin in Littleton, Colorado, and I'll talk to you about the scientific payload, which has some great representation across the state of Arizona. This is our sample collection mechanism here. We call this the TAG-SAM, or the touch and go sample acquisition mechanism. This filter head is the only thing that'll make contact with the asteroid surface, which we expect will take about 5 seconds to collect our material. And I'll go through why that's the approach that we took for the design of this mission. Of course, I'm here representing the work really of thousands of people all around the world, with a huge concentration right here in Tucson, Arizona. This is a $1 billion program in the NASA New Frontiers mission line, which is kind of in between the smaller class discovery missions and then the really large flagship missions. $200 million was direct contract work to the University of Arizona. I have a staff right now of 70 full-time employees and lots of students, undergraduates and graduates. I think we're up over 200 students have had real hands-on experience working on this program. And this is just a snapshot of the team here at the University of Arizona that is working on this program. It's a very diverse team in terms of age, in terms of gender and backgrounds, and that's something that has been a real honor to lead this group of people and to see students grow up. I've been working on the program for 16 years. I've been a professor at the University of Arizona for almost 19 years. And I was one of these students back in 1988. I graduated from U of A in 1993 with a Bachelor of Science in Math and Physics and a Bachelor of Arts in Humanities from the East Asian Studies program. So it's great to pay it forward. I got my start in planetary science through the NASA Space Grant Program, and I know a lot of the organizations here in Southern Arizona sponsor Space Grant interns. See, Grant Paragon has been a great supporter of the Space Grant program. Keep doing that because it really does make a difference to these kids. Just the gleam in their eye when you tell them they can come and work on a NASA program is worth its weight in gold for sure. So the mission name, as I like to say, is an awesome acronym that is entirely my fault. So it captures the real scientific objectives of the mission. It's an origins mission. We were talking at the breakfast table. I was with the insurance crew in back there. And, origins is going back to an asteroid that is dating from the formation of the solar system 4.5 billion years ago. We're basically geologists. We like to look at rocks. We like to analyze them and tease out their secrets. These are the oldest rocks in the solar system. You can't find rocks this old on the Earth. You can't find rocks this old on the surface of the Moon because that record has been wiped out through geologic processing over time. So we're going back to the dawn of the solar system. We use spectroscopy. We have all these amazing telescopes on the mountains around Tucson. Spectroscopy is basically passing light through a prism, breaking it up into its wavelengths, looking at the different colors and seeing which ones are bright, which ones are dark, and that tells you a lot about the chemistry and minerals on the surface. There's over now 700,000, maybe 800,000 catalog asteroids in the solar system. We're not going to send a spacecraft out to every one of those. This is how you ground truth that remote sensing capability. I see Vishnu is here in the audience. He's one of the world's experts in asteroid spectroscopy. He wants to know exactly what this asteroid is made out of so that he can interpret the hundreds of thousands of other objects in the solar system and figure out what they're made out of as well. Back in 2004, when I came up with this name, I put down resource identification. And I thought, I'm just going to let my sci-fi freak flag fly, right? So I want to go mine asteroids. I'm not going to be shy about it. But I thought, I'm never going to be able to do that, but I'm going to maybe get a spacecraft out to an asteroid. And then I saw a bunch of startups in the United States and around the world go into asteroid mining, and then I watched them all go bankrupt. So it's been a real interesting cycle so far. I still have hope that that idea will be resuscitated at some point in the future. Security is a big one. This was intentional, political, to indicate to Congress, which every time they write a NASA Authorization Act, says that NASA shall be responsible for documenting and determining the risk to the Earth from asteroid impact hazards. We're going to the #1 asteroid in terms of its likelihood of impacting the Earth. We are very much aware of the security implications. We want to understand its orbit. We want to understand its composition so we can do something about that. In the early days, the program was just called OSIRIS. We were at a smaller budget level. We grew up into the New Frontiers program, basically doubled the budget to the $1 billion mark. I needed a name that indicated that we were bigger and stronger and better than OSIRIS. And as a joke, one of the team members threw out OSIRIS-REx, and we laughed, and then I was like, man, that sounds really cool. And I said, that's got to be the name of the mission. It sounds like a dinosaur, and that's what we want to be all about. Everybody knows how the dinosaurs ended their days, right? So this is my backronym, the Regolith Explorer, fitting into the Rex idea, and regolith is what we call the material on the surface of the asteroid, so it made a lot of sense. So we knew a lot about this target before we launched. So these are radar data from the Arecibo Planetary Radio System in Puerto Rico. And then we're able to process that data to build a 3-dimensional model of the asteroid. Its size is about 500 meters. It's about the size of Push Ridge, if you need a local analog. So it's like a small mountain floating in outer space. We know how fast it's spinning. We had a pretty good assessment of its density. This number may not mean anything to you, but your average rock would be 3,000. And this asteroid is 1260, so it's less than half the density of rock, which is great because we're really interested in organic material, carbon-rich material. We're going after origins, and we're even thinking maybe these things had a role in the origin of life. And this low density was one of the reasons we did that. And it's also very dark. The albedo, 4.5%, that's how much light is reflected off its surface. 4.5% of light is reflected. It means 95.5% is absorbed, a very dark black material. You can see its orbit over here in blue. Here's the orbit of the Earth in green, and you can see, sure enough, even when you look obliquely, this asteroid's orbit crosses right through the orbit of the Earth. Sometimes it even flies in between the Earth and the Moon, so it does get very close to us. It also gets very far away from us. It gets almost out to the orbit of Mars, so it's on a very elliptical orbit. This is the vehicle at Kennedy Space Center right before launch processing. I had the great experience of spending 3 months in a condo in Cocoa Beach as we were going through the final stages of launch processing for the spacecraft. I brought my whole family, my 2 kids, my wife, and I brought my mother-in-law to watch the kids, and my wife and I, who's also a planetary scientist and runs a small business here in Arizona, went to work at Kennedy Space Center every day. It was really a dream come true. So we launched in September of 2016. We had a 2-year-plus outbound cruise, including an Earth gravity assist in September of 2017, which got us this change in the plane of the orbit. You can see the asteroid is up a little bit from the Earth. And then we arrived in late 2018, and we're planning on sampling. We actually pushed this to August of 2020, so that's an exciting event coming up this year. And then we leave the asteroid in 2021. It's a 2.5-year cruise home, and we drop the sample return capsule off on a parachute system into the Utah Test and Training Range just to the southwest of Salt Lake City. And that'll be a big VIP event the University of Arizona will host. If you're interested in that, let us know. We would love to have you join us. These are the payload or the science instruments that are on the spacecraft. Here at the University of Arizona, we built the Polycam, which is the big kind of telescopic imager. We call it the Polycam because we can put in a focus mechanism and turn it into a microscope to get really high-resolution shots of the surface. Our mapping camera, which has a series of color filters to give us the color information, and the sampling camera, which documents the contact with the asteroid surface. Our friends at Arizona State University built the thermal emission spectrometer. They're world's experts in this technology, and so we called up Phil Christensen and asked him if he could provide this device for us, and it's been a lot of fantastic information coming out of that. A visible and infrared spectrometer from the Goddard Space Flight Center, and a laser altimeter from our partners at the Canadian Space Agency. And then we had a student experiment from MIT and Harvard looking at X-rays coming off the surface of the asteroid. Very capable scientific payload, and it's done a great job mapping the surface of the asteroid. This is the shape that we determined from the laser altimeter. You can see we did a pretty good job from the ground-based radar data that we actually really did nail the shape. The density turned out to be even a little lower than we had estimated from the ground. And when we look at it in detail, this is not a solid, coherent body. This is a pile of rubble. These are boulders and gravel that are loosely bound together in space, which is why they get this almost spherical shape. This is a very small body. You wouldn't expect it to turn to a sphere like a planet. That requires it to be liquid. But it's kind of behaving like a liquid. Rubble in microgravity, when you spin it up, we call this a spinning top shape. And it turns out a lot of the near-Earth asteroids have this structure. These are just some of the shots from the asteroid surface. So the idea is, so notice the field of view here is almost 70 meters across. So you're looking at some pretty large and rough rocky surface. Our sample mechanism is about 30 centimeters across. It's designed to pick up loose gravel. There's not a lot of that on the surface of this asteroid. This is a much rougher, rugged environment than we had designed the spacecraft to go and sample. There are some glimmers of hope. In fact, this crater back here was one of the potential sample sites. So you can see some fine-grained material in here. This is only 20 meters across. That's much smaller than the guidance system that we designed on the spacecraft. So we have a real challenge ahead of us to get into a tight spot on this asteroid, basically requiring precision guidance on the vehicle. And the asteroid has continued to surprise us. We went into orbit on December 8th, 2018. And then starting in early January, we noticed these eruptions or ejections of particles coming off the asteroid and spewing into outer space, which really shocked us and surprised us, required a huge safety analysis for the vehicle to make sure that we weren't in any danger of losing the spacecraft. Turns out that they're pretty small. They're on the order of centimeters, maybe up to about softball size. And they're moving relatively slowly. So the spacecraft is designed to take hits from micrometeoroids, and these didn't pose a risk to the spacecraft. But they presented a really amazing scientific opportunity. I guess this, see if we can, there we go. These are all the particles that we have observed around the asteroid. Some of them are going into orbit. So this thing is surrounded by a cloud of particles. Some of them are being ejected into interplanetary space. Some of them orbit the asteroid for a while and then re-impact. Here's the spacecraft orbit around the asteroid. So these turned out to be free gravity probes for us. These things, some of them are even bouncing off the surface and then going back into orbit. So this has been a fantastic science experiment, totally unexpected, but a real bonanza. And we have just submitted a dozen papers. We published in Science in December, the discovery, and then we put in a dozen papers into the Journal of Geophysical Research, and we have a special issue on this totally unexpected phenomena. This is just an animation of the sample strategy. So here's the sampling head coming down to make contact with the asteroid surface. The idea is that we're going to contact for about 5 seconds. It's basically an air filter. I like to say it would look right at home on the carburetor of a 57 Chevy, basically the same technology. And then there's no air on the asteroid, so we bring bottles of air and we shoot those down into the gravel, and that pushes everything up through that filter, and then the material gets collected. Once we verify sample, we go ahead and put it into a sample return capsule. Opens up like a clamshell. We'll actually separate the entire filter is what we'll be bringing back to the Earth, and that capsule is the only thing that makes it back to the surface. So we'll bring the spacecraft back to the vicinity of the Earth, and then just like a quarterback, we're going to spin that capsule up and we're going to throw it at 28,000 miles per hour. It'll enter the atmosphere targeting that Air Force range in Utah. So in order to get the sample site identified, we had really 4 criteria. We had to make sure we could deliver it to a safe location where there was material that we could sample that had the highest scientific value. So this is the global data set. This is a combination of the laser altimetry data from the Canadian Space Agency instrument combined with the amazing cameras that we built at the University of Arizona. And when we combined those two, we did a thorough assessment of the surface. We had our final 4 sample sites, and we announced the winner in December. So you can see we're going after mostly these small craters, which seems to be where fine-grained material is accumulating. There's very little of this on the surface. This is the wall of a much larger crater, and it seems like it was shielded by this large boulder here, so it prevented all these other rocks, which are kind of in a low-speed, slow-motion landslide down the wall of that crater right there. But this little swath seemed to be protected from all of that. You can see that there's a lot of rocks and large hazards around some of these things. One thing we worry about is when the spacecraft makes contact, it may tip over as much as 25 degrees, and then we're just going to fire the thrusters to get away from the surface of the asteroid. And so we have one hazard here that I've nicknamed Mount Doom. It's about 20 feet tall, 7 meters tall. And the nightmare scenario is you would land in this crater, tip over, and then crash into that thing on your way out. So those are the kinds of things that we worry about constantly. We did select that crater with Mount Doom as the primary sample site. We had to go to NASA headquarters with Thomas Zurbuchen to get confirmation on that. This just shows you what we expected. I even used the word beach a lot during development when I was presenting to the Standing Review Board and to NASA headquarters. All of the astronomical data suggested that this thing was very smooth and that the average particle size was on the scale of a centimeter or so. This is a 5-meter scale bar down here, so you could say this is a 7-meter boulder here. So we were looking at a 25-meter radius guidance accuracy that we designed the spacecraft to. We're now looking at having to get within a 5-meter location. So we have completely changed the guidance system on the spacecraft. We were using a LiDAR-based system. We are now going to onboard natural feature tracking, which was a flight software change. But now the spacecraft autonomously is taking images all the way down to the surface, identifying features in a catalog that we've uploaded to the memory banks of the spacecraft, and then determining how it needs to fire its thrusters for a precision guidance. It's like a guided missile, or a smart dart, as we like to say, but it's 150 million miles away from us. This is just to show you that even if there are large rocks, this is testing of the sampling mechanism in a reduced gravity environment. We are required to bring back at least 60 grams, which is about a coffee cup full of material. The engineers designed it to pick up over twice that amount. And even in the case where there's large rocks obstructing the filter, we still exceed the design requirement. So we're confident if we can get the spacecraft to that crater site, then we will be able to collect the material and meet our requirements. These were the final 4 sites. Bennu is the name of the asteroid. I'm not sure if I said that yet. Bennu is an ancient Egyptian bird, heron from mythology. So all the features on the asteroid are named after birds or bird-like creatures, mythological creatures. So we had these 4 sites, and as I mentioned, the Nightingale site is the one that we selected as our primary target. This just kind of shows you how we did some of the assessment of the asteroid surface. So once we got to the final locations, we mapped every rock that we could see down to the centimeter scale. So we had a team of undergraduates that we trained in image analysis, and they sat there for days and days on end, literally measuring on the computer the longest axis on thousands and tens of thousands of rocks across the asteroid surface. God bless them. They really did a great job for us. So anything that's larger than 20 centimeters is a hazard, and it's marked in red. That would just block or clog the filter, and we wouldn't be able to get any material around it. And then we also worry about the tilt on the asteroid surface. If we come down at a really high tilt, then the spacecraft will tip over, and we're in that hazard situation. So you can see the final 2 sites, the Nightingale site and the Osprey site. Osprey site has a lot of hazards in terms of collecting material, even in the center. These circles are the likelihood that we're going to hit. So the yellow circle, it's a little hard to see the different colors. The inner circle is 80% chance of hitting inside of here, and this one is 99% chance of hitting inside the larger circle. So overall, the Nightingale site has a much smoother area and more likely if we make contact with the surface to collect that material. And then this just shows you the hazard maps. So this is what the spacecraft will have on board. So as I mentioned, we worry about tipping over. So even this swath looks fine if we touch there. But the problem is if we touch there, tip over, and fly away, then we crash into Mount Doom. So there's these other areas that we could tip over and make contact with the spacecraft that we worry about. So the spacecraft will be coming down, and it'll be calculating on board where it's propagating its state all the way down to the surface. And if it's propagating down, it says, I'm going to contact this area. It has this hazard map in its memory. It'll say, nope, this is no good. It has the ability to call a thruster fire and back away from the asteroid surface. It's not like a Mars landing where it's one and done. We can stop, we can fly away. We're kind of like a hummingbird. We can zip around this asteroid, get it from all different angles. We can go back and we can try it again. It takes a long time to set that up, but we can do it. So then just looking out, 2020 is the year of TAG. We're going to have a lot of fun with that theme, so please follow along with us. We're very active on social media. We have a great website. President Robbins does a great job promoting the mission to local community groups. And I'm also available if you have a group that you would like a presentation to. Just get in touch with me after the meeting. So we have a whole series. We're going to continue to characterize the primary and the backup site, Nightingale and Osprey, at ever lower distances from 625 coming up in a week down to 250. And then we start rehearsing the different phases of sample collection, getting really close within 100 meters, getting within 50 meters. And then our first sample collection attempt is scheduled for August 25th. So pay attention. That should be a great day in space exploration history for the University of Arizona, for Tucson, for our state, for our nation, and for the world. Thank you.